Okay, now we're going to talk in this screencast about electric circuits. We've learned in the last screencast how to calculate the amount of force on charges when they're in the presence of another charge, either a like charge or an unlike charge. We would use Coulomb's law, that equation that looks a lot like gravitational, universal gravitational force, to calculate the amount of force exerted on charges. Well, in an electric circuit, you've got a battery that actually has done some work to separate some charge using its chemical potential energy. So you have one side of a battery where there's a bunch of positive charge built up, and another side of the battery where a bunch of negative charge is piled up. So the battery, the symbol for the battery are the two lines. Sometimes there'll be four lines. It'll be like this. You know, it's the same idea. Maybe it's just a more powerful battery, but a long line represents the positive terminal of the battery. The short line represents the negative terminal. And in a battery, the chemical potential energy is used to pull the electrons from the one side of the battery chemically. So it strips the electrons off of the atoms, so you leave a bunch of positive ions on one side, and you have an excess of electrons on the other side. And it happens through chemical reactions, and only electrons can move in a conductor. So in a metal conductor like a copper wire or a silver wire, for instance, the reason they're conductors is they have some free electrons that are free to move. So the only charge that actually moves in a circuit is actually a negative charge. Our convention, though, is to show current moving from the positive side to the negative side, because that's the way Ben Franklin, who was the original guy that invented the positive and negative charge, thought that charge moved. He thought that the positive charge was the one that moved. So our convention is we show the current going like this, from the positive terminal of the battery to the negative terminal. Current is represented by the letter I, capital I. It's measured in amps, which is just an A. Excuse me. So the current in this particular circuit is going to move in a clockwise fashion from the positive terminal. It's going to move all the way around here to the negative terminal, clockwise. All right, and it's going to pass through these squiggly elements, which are called resistors. A resistor is kind of like what it sounds like. It resists the flow of charge through it. So it's kind of like a constriction in a pipe. In fact, you can think of an electrical circuit as a piping system. The battery is like the pump that pumps the water through the pipes. The copper wire, in this case, would be represented by these black lines, and that would be the pipe itself. And the charge that moves through the conductor would be like the water going through the pipe. And these resistors would be like constrictions in the pipe, where the pipe narrows down, so it's harder for the water to get through. So that's kind of what a resistor is. Resistors are, the symbol for resistor is a capital R. It's measured in ohms. Both amps and ohms are named after an actual guy. And the symbol for an ohm is an omega, a Greek letter omega. And batteries are measured in volts. So you might have in your calculator 4 1.5 volt batteries. It's not uncommon to have 12 volt batteries. And your car has a 12 volt battery. These are direct current batteries, DC batteries. So alternating current is what you have in your house. But in these simple circuits, everything we work with, when we're connecting to a battery, that is called direct current. So DC circuit. This is a DC circuit. Okay. And a battery is a source of energy. Okay, it's a source of power for the circuit to allow the current to flow. So it's basically like a pump in a piping system. I'm going to show you a little bit more complicated circuit to illustrate a point about how current flows through a circuit when it's got an option. Notice how here the current doesn't really have a choice of where to go. It's going to flow from the positive terminal to the negative terminal, following that convention I mentioned. And it doesn't have any other branches to go through. It's going to pass through, I'll call this R1, I'll call this R2, and I'll call this R3, the three resistors. are going to have the same amount of current going through them. There are no branches for the current to branch off to, so when all the resistors have the same current going through them, it's a series circuit. All those resistors are in series because the current has only one path to follow through those resistors. I'll show you a circuit on the next page where the current has more than one option. Okay, so here's my positive terminal in my battery, here's my negative terminal. I'm going to have current flowing from positive to negative. I'm going to call this amount of current I1. You'll see why I have to designate the currents I1, I2, because as the current passes through this resistor, the current leaving the battery is I1. The current, all that current has to go, all that charge has to go through the first resistor. Let's call that R1. Let's call this R2. Let's call this R3. Let's call this R4. See if I can erase it. Yeah, so I'm going to put it up here so it doesn't get in the way in a minute. All right. So here's a junction up here where I put that red dot. Okay, that's a junction where I1 has a choice to pass through R2 or R3. So the current is going to split. You're going to have some current go through this branch. You're going to have some current go through this branch. I'll call it I2 and I3. So I2 passes through R2, I3 passes through R3. Just like you can imagine water that's running through a piping system that gets to a branch in the pipe, all of the water that comes in is going to go through one of the two branches. So not surprisingly, you know, charge is conserved. So whatever amount of current comes into I1, then that current has to split into either I2 or I3. So I1 is going to be equal to I2 plus I3. Now we keep following this through here. This is going to be I3. It's the same amount of current that came into resistor 3. It doesn't have anywhere else to go. So it comes down to the bottom here to this junction point. I2 is going to continue on to this junction again. So now you've got I2 and I3 coming together at the bottom junction point here. So they are going to combine again to form I1. So I1 is going to pass through resistor 4. So again, I1 is going to be equal to I2 and I3 coming together at the bottom junction point. So that same current, I1, is going to pass back into the negative terminal of the battery. So it's like, again, the battery is like a pump. If you want to continue to pump water through the circuit or pump water through a piping system, you have to have just as much water come in as goes out. So it's a pretty good analogy when you think of a piping system. Okay. Because this circuit is a little different, when you get to this junction point up at the top junction point right here, sorry about that, this top junction point right here, because the current has a choice of which direction to go, and then it comes back together down here. Because there is a choice of which branch to go through, this is not a series circuit. We say that R2 and R3 are in parallel. So this is actually a parallel arrangement. Actually, I probably shouldn't say it's a parallel circuit. Sorry about that. I'm going to say the two resistors, R2 and R3, are in parallel. It's not a parallel circuit per se because R4 and R1 are technically in series because the current doesn't have anywhere else to go, but all I1 is going to pass through R4 and the same amount of current is going to pass through R1 after going through the battery. So it would be wrong to call this just a parallel circuit, but you could say these two resistors specifically are in parallel, 2 and 3. Okay, that guy and that guy. Okay. So what is a resistor? A resistor is anything that draws down the power of the battery. And in our houses, all the things that we use in the electrical circuit draw the power from the source, which is coming from the electrical company in your house. But when you turn on a light in the house, the light acts as a resistor, so it's using up energy. The toaster in your house acts as a resistor. When you turn on your computer or your TV, it's using power, it's using energy, electricity from the electric company that acts as a resistor. Okay? Well, certain resistors follow a law called Ohm's law, and I'm going to teach you how to apply Ohm's law. A lot of the things that you use in your house do not follow Ohm's law, like I'll explain later, but sometimes little light bulbs, we'll maybe do a demonstration in class with a light bulb. They don't follow Ohm's law because they heat up and their resistance changes when they get hot. But all the resistors that you're going to work with in AP1 will follow this law called Ohm's law. Ohm's law is basically V equals IR. V is the voltage of the battery, equals I, which is current times resistance. Okay. Not all resistors follow Ohm's law, only resistors that are ohmic follow Ohm's law. Let me just, ohmic resistors. Okay, so all the resistors that I'm going to teach you about will follow Ohm's law. You probably will need to be aware conceptually for the AP test that there are such things as light bulbs that when they heat up they don't follow Ohm's law, but for the most part everything we talk about is going to follow Ohm's law. And here's why this is a useful law. It helps us to analyze a circuit and to figure out how much current is going to go through different branches of a specific circuit. So let's take a look at a simple series circuit here. Okay, I got a simple circuit down here. It's a 9-volt battery. There are 3 resistors. There's a 2 ohm resistor on top, a 3 ohm resistor off there on the right, and a 4 ohm resistor down at the bottom. So this is a series circuit. So the current is going to come out of the battery, out of the positive side, right? And it's got nowhere else to go, right? It's going to pass through the 2 ohm resistor. I don't even need to call it I1. I'll just call it I. It's all the same throughout. Okay, so I passes that way, comes down this way, and is going to pass right back in here. So it's going to follow a clockwise path. Well, it turns out that every time the current passes through a resistor, the voltage drops. So you've got a change in voltage across each one of these resistors. So I've got a delta V in the 2 ohm resistor. I've got a delta V in the 3 ohm resistor, and I've got a delta V in the 4 ohm resistor. And it turns out that the combined voltage drop across all 3 of those is going to add up to the 9 volts. Think about it like there's a certain amount of energy that the 9-volt battery's got, a certain amount of power, and that energy is going to be used up as in its entirety as the current is pushed through those resistors. So the V2 plus V3 plus V4 is going to add up to the 9 volts. Okay, so that's the equation there. Delta V2 plus delta V3 plus delta V4 equals 9 volts. What we're going to do is we're going to use this Ohm's law. The reason Ohm's law is useful is that if you know the amount of voltage you have in a circuit and you know the amount of resistance is in that circuit, you can figure out how much current is passing through the circuit. Knowing the amount of current going through a circuit is very important. It's important in your house because wire is sized based on the amount of current passing through it. You don't want to have a real small wire with a lot of current going through it because it'll heat up, it could cause a fire. That's like trying to push a lot of water through a tiny pipe. You know, you're going to have problems, the pipe might burst. That's kind of like what happens when you try to push too much charge, too much current through a wire that's not sized correctly. Also, in your house, you have circuit breakers that are designed to actually trip or break the circuit, actually. So it basically is like a switch that disconnects the circuit when too much current is flowing through it. So it senses how much current is going through the circuit and trips and breaks the circuit so that the wires don't heat up and cause a fire. So we're going to use Ohm's law to actually calculate how much current is passing through our circuit here. And here's how we're going to do it. We're going to apply Ohm's law to each one of those little resistors. So delta V2, for instance, is equal to the current I passing through R2. Delta V3 is equal to the current passing through resistor 3, or the 3 ohm resistor. And delta V4 is equal to the current passing through the 4 ohm resistor. And you know they all add up to the 9 volts. So let me see if I have some room down here. I'm going to have to rearrange some things. Okay, so I know, starting off with this equation right here and substituting in the delta V2, V3, and all those terms, I'm going to say I R2 plus I R3 plus I R4 should add up to the 9 volts. But notice that it's the same I in all of those individual resistors because it has nowhere else to go. That current has nowhere else to go but through the clockwise path. So 9 volts, if I factor out the I, R2 plus R3 plus R4, which is 2 plus 3 plus 4, right? Having a hard time making my 4. Here we go. And I will take that onto the next page. So I've got 9 volts equals I times 2 plus 3 plus 4 ohms. So that is I times 9 ohms total. And I is going to be equal to 9 over 9, or 1 amp. Also, I could have just said 1 capital A, amp. Okay, and so now I know how much current is going through that circuit. So each resistor is going to have 1 amp of current going through it. And that allows me to size the wire. It allows me to design a circuit breaker of the right size to put into that circuit to trip if there's more than 1 amp going through the current or through the circuit and it's designed for 1 amp. The wire is designed for 1 amp. I might have a circuit breaker to trip with a little more than 1 amp. Now, this part of the equation up here is called the equivalent resistance of the circuit. Okay, and for any time you have a series circuit, you can find the equivalent resistance by simply adding up the resistors in series. So I'm going to make the symbol like this. R equivalent equals R1 plus R2 plus R3 plus ... as many resistors as you have in the circuit, and this is a general equation for a equivalent resistance in a series circuit. So this is for a series circuit. Okay. As you might guess, there's going to be a different formula for a parallel circuit because the current doesn't have only one option in a parallel with parallel resistors. The current has 2 different branches that can go down. Okay, so here's a parallel circuit, and we'll talk about how to calculate equivalent resistance in this circuit. I'm going to say this is a 2 ohm resistor here, and we'll call this a 3 ohm resistor here. Let's make this a 9 volt battery. Positive side here, negative side here. So we've got I1 that comes through the top, comes to a junction right here, and I could have I2 here, and I could have I3 going this way. So I know that I1 splits into I2 plus I3. Okay, well, it's useful to think of this battery as having 0 volts on the negative side and a positive 9 volts on the positive terminal. So when you think of it that way, then the wire, basically, you're not going to lose any voltage in the wire. We're going to pretend it's an ideal wire with no friction. If you want to think of resistance as friction in a system, we can assume that you still have your same 9 volts at this point right here, and you've got 0 volts down here at the bottom because this is at the same point in the branch as the negative terminal of the battery. There's no resistors between those two dots, so there's no place to lose voltage across that wire. So if the negative terminal of the battery is 0 volts, then this junction also has to be at 0 volts, and this junction would also be at 0 volts, and this guy up here would be at 9 volts, just like the junction right here. Okay, so the two top junctions are both at 9 volts. So what that lets us do, and it looks like I'm making some stray marks down here, sorry. Now we can do a little circuit analysis with that information. What we're going to say is that across the 2 ohm resistor, hang on. Sorry, I'm going to start with this right here. So I1 equals I2 plus I3. Okay, so I2, I'm going to do this off on the side. The amount of current going through I2 is just the voltage across that second resistor divided by R2. So I'm applying V equals IR, but I'm solving for I. So I'm dividing both sides by R, and I get I equals V over R. So the change in voltage from 9 down to 0 across the 2 ohm resistor is going to tell me how much current is in that branch. Likewise, I3 would be the voltage drop across resistor 3 divided by how much resistor 3 is. So, so we have here the 9 volts, I'm sorry, I1 Okay, I just rewrote some stuff over here, but I want to look at the whole circuit, and in order to come up with an equation for the equivalent resistance, I know that my change in voltage across the battery, my 9 volts, is going to be equal to I times R, with I1 being the current coming out of the battery and going into the battery, times R, which would be the equivalent resistance of the whole circuit. So when I solve for I1, I get the delta V9 over R equivalent equals I1. But I also know that that equals I2 plus I3 from this expression right here, okay, which is delta V2 over R2. Oops, sorry, I'm having a hard time down in these little corners down here. R2 plus delta V3 over R3. I'm going to take this, I can stay on this page right here. Okay, and I know that delta V2 and delta V3, the voltage across those two branches, are all 9 volts, from 9 down to these zeros down here. Okay, so I can factor out the delta V. So I have delta V times 1 over R2 plus 1 over R3 equals this delta V9 over R equivalent. Well, this delta V is 9, this delta V is 9 volts. These two cancel out. So now I've got an expression for my equivalent resistance. 1 over my, this is going to simplify to 1 over R EQ on this side. So going to the next page. 1 over the equivalent resistance for a series circuit is just equal to the sum of the inverses of the resistors that are in series, plus dot dot dot. That's the general form of the equation for resistors that are in parallel. So for our our circuit, 1 over Req would be equal to 1 over R2 was 2 ohms plus 3 ohms, which that would be 3/6 and 2/6, which would be 5/6. But remember, that is 1 over Req, so Req would be the inverse of 5/6. So the equivalent resistance would be 6/5 of an ohm, or 1.2 ohms. What that means is those two resistors that we showed there are the same as a circuit that would look like this. Instead of having a 2 ohm resistor like that and a 3 ohm resistor like this, and 9 volts here, it's the same as a circuit that has a single resistor of 1.2 ohms. So the amount of current going through my circuit I can calculate very easily. Current is equal to the voltage over the resistance, which is 9 over 1.2, which, let me go offline just a second, that is 7.5 amps. So now we know how much current is going through, coming out of the battery. It's 7.5 ohms. How much of that current goes through the 2 ohm resistor and how much current goes through the 3 ohm resistor? We'll look on the next slide for that. You would expect, since 3 ohms is a bigger resistor than 2 ohms over here, that you'd expect more current to go through the 2 ohm resistor since it's less resistance. And that's in fact what happens. I'm going to redraw it on the next page. Okay, so here's our 7.5 amps that's coming out of the battery. That's I1. Now we've got I2 going this way, and we've got I3 going this way. They have to add up to I1. Okay, well, I2 is just going to be equal to voltage across the second resistor divided by the resistance in the second resistor, or the 2 ohm resistor. And we have already said we have 9 volts from this point up here, from this junction down to this junction. It's a 9 volt difference provided by that battery. Same 9 volts as you have across those two junctions as well. So 9 volts divided by 2 ohms is 4.5 amps passing through this one. So this has 4.5 amps here. This guy here has 9 volts divided by 3 ohms. It has 3 amps. And sure enough, these two add up to 7.5 amps. So when they come back together, you have your 7.5 amps again coming back into the battery. So now we know how much current is going through each individual resistor, and we can size the circuit breakers appropriately. Next screencast, I'm going to talk about circuits that have little series and parallel resistors both in the same circuit. They're called combination circuits, and I'll show you how to analyze those.